Hello, welcome to my vlog for the introduction to complex numbers. So when we say complex numbers, this is actually a mere one of the topics for basic algebra. But the entire context of the fact that we're studying the complex numbers is actually in the concept of complex analysis. But since this is just a mere introduction, so we're only dealing with basic algebra, so everyone can relate with this. So what is really in a complex number? So complex numbers can be defined as ordered pairs x, y, provided that your x, y are elements of real numbers. And these numbers are to be interpreted as points in the complex plane with rectangular coordinates x and y. Now, we denote the set of complex numbers by the symbol as this one. So it's like a letter C with a double something. These are, however, is actually the set of real numbers. Now, in this topic, we assume that you already have a background or a knowledge for the real numbers. Otherwise, you have to double check or review on the videos I have for the real numbers. So let's consider this for this illustration here. I have here the x. This is x into y here. So if you notice, the points that you found in these horizontal axis are actually the points x0, and the points that you will find in these axes here is 0, y. Now this x0 will only tell us that the second ordinate is actually 0, so that means there's no value for y. So this actually represents the real entries or the real numbers. This, however, doesn't have the real entries, but an imaginary entries. So technically, this x-axis represents as the real axis, and this y-axis represents as the imaginary axis. So now, why are we talking about the imaginary axis? This is actually this complex concept is in the idea that we're actually looking for the solution. Say for example, we have sorry, let me write it in here. Let's say for example, we have x squared equals 1 equals 0. So if we are going to solve for the value of x, this should be x squared equals -1. And so this implies that x is equal to plus or minus the square root of -1. Now, in the context of real numbers, observe that if the index of the radicand here is even, so we're pretty sure this is even because this is 2. So we must have to have the value inside the radical sign as something, let's say, a greater than or equal to 0. But in this case, it is less than 0. So this is no longer a real number anymore. That's why we call this as imaginary number. So this is where the rise of the study for the complex numbers. Now, sorry. Now, if we denote this C here, let's say now if C here is an element of a set of complex numbers, it is customary to denote that we can write Z equals X and Y here. So this is actually the value with rectangular interpretation or complementation to the x-axis, and this is for the y-axis. So here, the x here is what we call the real image. We denote this as re of z equals x. Y, however, is actually the imaginary image, and we denote this as im of z equals y. So for simplicity, since this is actually our z equals x plus y, so for simplicity, we can write our z as x plus iy, where our I is equal to the square root of -1. Okay. Now, of course, in the notion of the set of complex number, of course, we have a binary operation with that. So define the binary operation as this one. So given that you have two complex numbers, the z1 and the z2, we have the sum as z1 plus z2. So of course, we are going to get the sum of these ordered pairs. So this is actually the answer. So this is actually the sum. Now, if we have to get the product of z1 and z2, then we will get this here. So let's consider, for example, let's say we have z1. This is 1, 1, and our z2 is equal to 1, 2. So basically, we can write this as 1 plus I, and this is 1 plus I2. So to get the sum of z1 plus z2, so we will have to, as according to the definition, we're just going to get the sum entry wise. So basically, we only have to add the entry wise here. So I'll get 2, 3. So that is actually the sum of z1 and z2, or we can write this as 2 plus 3i3 or 3i, depending on your orientation. Now, if we have to get the product of z1 and z2, so basically, we only have to follow these formulas. This is actually x1 and x2 and 3 here. So we'll multiply 1 1 here. So I'll get 1 minus the product of y1 and y2. So this is 1 and 2. So that's 1 minus 2. So you get 1. And you have to get the product of y1 and x2. So that's y1 here. So 1 and 1. So that's 1 here. And x1 and y2. So that's 2. So that's a 1 plus 2. So you get 3. Or you can write this as -1 plus I3. That's it. Now, of course, in the concept of the set of complex numbers, we have actually the following properties. So first is we have the so-called commutativity. So when we say commutativity, it's actually let me show you as not to annotate here. So when we say it's commutativity, we have, let me write in here what happened. Okay, here. So when we say commutativity, say for example, you have real numbers z1 and z2. So we say it's commutative if we have z1 plus z2. This is just equal to z2 plus z1. So they're actually commutativity because let's say, for example, you have z1, which is equal to x1, y1. You also have z2 equals x2 and y2. So if we are going to just add with these, I can have x1 plus x2, and I can have y1 plus y2. But observe that these x sub i's and y sub i's here are real numbers. And we already know from the concept of real numbers that real numbers are commutative with respect to addition. So we can commute this one. And so therefore, this is just the same as z2 plus z1. So this actually follows for commutativity for multiplication as well for the set of complex numbers. So you can verify it on your own, or if you have question, you can comment down there on the comment section of the video. Now, another is associativity. So associativity tells us that if you have three complex numbers, so let's say z1, you also have z2, you also have z3. So z1 plus z2 here being grouped as this one, this is just the same result if we're going to get the value of this one. And this will also hold for multiplication. So if you have z1 times z2 here times z3 here, so it's just the same as z1 times z2 times z3 here. So you can verify it on your own as well. But if you again, if you have question, you can comment down there so that I can be able to reply you with some solutions if I may. Another is the additive identity. So when we say the additive identity, so it's actually the existence of um, the identity at which, let's say if you have, so let's focus first on the additive identity. So given that you have z, you have a complex number z, there is this so-called existence of another complex number at which if you get the sum, you'll just get z. So basically what you can imagine is zero, and zero is actually correct. So basically our additive identity is of the form 0, 0. Why? Because if you're going to add z by 0, this is actually z. So that's an additive identity. Now what happened for multiplicative identity? So if we're looking for multiplicative identity, so let's say for example, you have complex number z. What are you going to multiply here to get the same result z? Of course, this is actually 1. Because 1, of course, is an element of a real number. And of course, we can write 1 as 1, 0, I. So this is just um, an element of complex number. And so our multiplicative identity is of the form 1, 0. Okay, next is the existence of additive inverse and the multiplicative inverse. So this is actually in connection with the identities prior. So if you notice, let me annotate here. So if you notice, our additive identity is our additive identity is 1. I'm sorry, 0. So this is actually in connection with getting the additive inverse. So suppose you have a complex number z here. What you're going to add here to get the 0, because our 0 is actually the additive identity. So what are you actually getting here is the additive inverse. So to get the additive inverse for that, of course, we can write negative z. What is really the additive inverse, not in the form of z? Now, let's say, suppose, for example, our complex number is xy. Okay. Now, what are we going to add to xy to get 0? So let's assume we have u v here equals 0, or actually 0, 0. So to get the entry wise here, so it's x plus u here. This is 0, and we also have um, y plus v here equals 0. So they're actually all real numbers here because we're actually what do you call this? Partition them into their parts. So we can have x equals negative u, and we also have y equals negative b, or we can simply right? U equals negative x, and so v equals negative y. So therefore, this our our additive inverse is actually negative x and negative y. Okay. Now let's go to multiplicative inverse. Now, multiplicative inverse, if we're going to solve on that, you can verify it on your own that the multiplicative inverse, let's say, what we're trying to do is we have, sorry, suppose you have z as a complex number, which is can be written as xy. So our multiplicative inverse can be this way. Um, we're going to multiply, let's say uv, and will have to get the multiplicative identity 1 0. Now our goal here is to find the value of u and v. Okay. Now observe that if we multiply these ordered pairs here, we can have x u minus y v equals 1, right? And we also have y u plus x b equals 0. Now solving for u, because we're actually looking for the value of u, this is just the same as u equals x over, correct me if I'm wrong, I can have, I'm sorry, this is, oh yeah, that's correct. So this is actually the same as x over x squared plus y squared. And this is, our v is the same as negative y over x squared plus y squared, which implies that the z inverse or the multiplicative inverse of z is x over x squared plus y squared and negative y over x, I'm sorry. So it should be negative y over x squared plus y squared. I'm sorry, I'm just to using this drawing tablet here. But if you have question for verifying all of these, you can comment down there on the comment section. Okay, so that's it. Now let's consider bunch of examples here. Let's say, let's show that this equality holds. Okay, so let's verify on that. So what I'm going to do is I have to simplify this, and my goal is to get the value for 2i. So observe that square root of 2 minus 1, I can have, I can multiply I here individually. So I'll get negative 1, negative I plus square root of 2 I squared, right? And remember, I squared is the same. I squared is negative 1. So I can have square root of 2 minus 1 minus I. I'm sorry, is this really okay? Square root of 2 minus 1 minus I plus square root of, I'm sorry, minus, okay, sorry for that. It should be, so it should be minus 2 square root of 2. So I have this. So this is basically negative 1 minus I. So what happened? Am I correct with the question? This is square root of 2. I think there is a mistake with copying the question. So that should be, We're trying to verify for. Let me make sure I copy the right question here. Sorry for that. Okay. Sorry, my bad. It shouldn't be this one. Okay, my bad. I'll just compensate you with the following with different questions. So it should be -1 minus I here. Okay? Okay, so let's go to example number 2. Let's show that re of IZ is equal to um negative imaginary of z. So let's recall that for our z, that can be written as x plus iy. This is our real image of z, and this is imaginary image of z. So this is just pretty simple. So to show that, so let z equals x plus iy. Okay, then re of iz is just the same as re of ix minus y, right? And so this is just the same as re of negative y plus ix. So therefore, this is now our real image here. So this is just the same as negative y. And um, the negative imaginary image of z, this is the same as negative im of x plus iy. So this is just the same as negative y. Therefore, the proof follows. Okay, let's consider another example. Show that -1 times z is equal to negative z. So let's let's prove on that. So observe that -1, I can write that as -1 plus I0, right? So I can have an ordered pair -1, 0. So if z is equal to x plus iy, I would have -1, 0 times xy. So basically, this is the same as -1 times z. So this is -1 times x minus 0y using the definition of multiplication. And I have 0x plus, oh, oh yeah, it's -1, y. So this is 0, this is 0, so I'll have negative x and negative y. I can extract negative here, so it's negative x, y, and so this is negative z. So the proof follows. Okay, so let's go to another example. One last example. Express this expression here, where of course your a is an element of real numbers, the set of real numbers in the form x plus iy. Now, what are we gonna do with that? Okay, so observe that I can multiply the denominator by its conjugate. That means I have to rationalize the denominator here. So remember that this is 1 plus a squared plus ia all over a minus I squared of 1 plus a squared. Now I can multiply these to get to rationalize the denominator. So I can multiply this by the conjugate. So that's a plus I squared of 1 plus a squared all over the same, right? The purpose why I'm multiplying with the same numerator and same denominator, it's because we're actually multiplying this by 1. You can't multiply the expression by any other value except 1 because you're actually changing the expression itself. Now, in this case, I'm just multiplying this by 1. Now, why did I come up with this expression? Of course, I'm just getting the conjugate of the denominator. Now, the conjugate of a minus I squared of this one is actually a plus I then this one. So therefore, if I'm going to multiply these, so sorry, I lost my pen. Okay, here it is. So I can have, I'm sorry. I lost my pen. This is my first time using this drawing tablet here. So, okay, so I have a square root of 1 plus a squared. And I also have a square root of 1 plus a squared. Plus, I have I a squared. And I have I 1 plus a squared. So you can verify multiplying this numerator here by using the definition of multiplication of complex numbers. Now, what is below is I'll just get a squared plus 1 plus a squared. This will be canceled here. And basically, if I'm going to add the numerator, I'll get, correct me if I'm wrong, it should be I to a squared plus I. And this, what is below is a squared. So it should be 2a squared. So I have 2a squared plus 1. And note that I can simplify the numerator by I times 2a squared plus 1. And I have 2a squared plus 1. So this will be canceled. So you're left with I. So I is just the answer. So we're done with just the basic of the set of complex number. So um, moving forward, I'm going to discuss another notion for the study of complex analysis. So thank you so much, guys, for listening, and have a great day to you.